Hello, Math Studies students, and welcome to your online lesson. Today we'll be doing our last video on our sequence unit, and here we will be covering geometric series. So our goal is to identify what a geometric series is and any associated formulas, and we'll know we're successful when we can find the sum of a geometric sequence using geometric series formulas. Quick reminder that an arithmetic sequence is a pattern with the same fixed number being added, or it could be a negative being added, which is like subtracted to get to the next term. And a geometric sequence is one where we are multiplying to get to that next term. We call the number that we are multiplying by the common ratio. To find our common ratio, we divide backwards. So we would take our second term and divide the first term, or take our third term and divide the second term. We have a formula. Anytime we are looking for a term of a sequence, we use this formula right here, our U sub formula, which allows us to find a specific term or U sub value by plugging in an N. Today we are going to be looking at sums. And so for a geometric series, we're finding the sum of consecutive terms in a geometric sequence. For a geometric sequence S of n, the sum of the first n terms can be expressed with the following formula. Now we can find this formula in our formula packet from the IB test, and we can also take notes on it right here. Now, the most challenging thing about this formula is the fact that the whole thing is basically a fraction or a big division problem. So when putting this in the calculator, we definitely need to be conscious of groups, especially the group in the denominator. So in your notes, you may even want to put a set of parentheses down there in the denominator just to show that we have to group those values together so that the calculator doesn't think we're just dividing by that r and not r minus 1. Most of these things should be familiar to us. R we saw in our most recent video, which was our common ratio. Again, we find that by taking any two terms of a geometric sequence or series and dividing backwards. We have our U sub 1, which we've seen throughout our unit on sequences and series, and that again means first term. And then we have our N value, which is the term number of the terms that we are adding up, or the last term that we are adding up in our series. So if I'm adding up, let's say, the first 7 terms of the series, n will be 7. And that same n is used here. And again, that's just a notation thing. We're not doing any math with that n here, but we would have s sub n. So if we had, let's say, 7, it would be s sub 7, which means the sum of the first 7 terms, just like it meant when we were doing that with arithmetic. All right, so let's try out this formula here on an example. So we have a geometric sequence that has all positive terms. It's important for us to know that so that we know that it's not going to be negative at any point or anything along those lines. The first term is 7 and the third term is 28. The first question is to find the common ratio. So let's start there. So that doesn't really have anything to do with our new formula per se, but whenever we are jumping terms, you know that I like to draw a little picture, almost like a hangman sketch. And our first term we know is 7. Our third term is 28. Now, since this is a geometric sequence, to go from one term to the next, we will be multiplying. And what do we multiply? We multiply our common ratio, or r. So 7 times the r value would get me to my second term. And then once I know my second term, I can multiply that by r as well. And so I'll be taking 7 times an r times another r, and that should get me to 28. So 7 times r, also known as r squared, is equal to 28. So I'm going to divide both sides by 7. I get r squared is equal to 4. And now I can essentially square root both sides. Now, whenever I write a square root, technically it could have a positive or a negative answer, but we were already told that all our values are positive here. So I am only going to focus on a positive 2. So our common ratio is 2, and we'll need that when we get to our next step. I'm going to clean up my work here. All right, for the next step, it says find the sum. Well, as soon as we see sum, we know that we are dealing with our S sub formula. And we want to find the sum of the first 14 terms. So I'm going to write down my S sub formula. I have S sub n is equal to U sub 1, parentheses, r to the n minus 1 all over r minus 1. So now we're going to start filling in some things that we know. Well, we're looking for the sum of the first 14 terms. So I can say that I'm trying to sum the first 14 terms right there. So my n is 14. Anywhere I see an n, I'm going to plug in a 4. I'm going to put 7 in place of u sub 1. Now my common ratio we just figured out, and that is 2. So I'm replacing r with 2 to the power of n, and we already showed that our n was equal to 14 because we're adding up the first 14 terms, as was shown here. So I have 2 to the 14th power. Minus 1. Now, remember this minus 1 here is not in the exponent like it was for a geometric sequence for that general term. Here it's just a regular minus 1 outside of the exponent. And then in the denominator, we have our common ratio once again, but this time not to an exponent, and then minus 1. All right, so at this point, our formula is done. We can plug it in our calculator. I might recommend, in general, taking your denominator. And since you're just subtracting 1 from it, even if it's a really high number, it's math that you can do in your head. So I'm going to have 2 minus 1 in my denominator, which is 1. And at that point, I don't even really have to plug that in the calculator, because when I divide by 1, it's an identity. Or to say that another way, it doesn't change anything. I can divide any number by 1, and the number stays exactly the way it was. In the numerator, I'm still going to have 7 times 2 to the 14th power minus 1. Now, some students might ask, can I subtract the 1 from the 2? And whether we're using Gemma or PEMDAS or some other shortcut for remembering our order of operations, remember you must do exponents before you subtract or any other operation. So I'm basically going to put all this in the calculator here, focusing primarily on my numerator, and then whatever I get there, I can always divide by whatever's in my denominator or put a 2 there, or just put this extra set of parentheses, which I'll show in green right now, around my numerator, and then around my denominator, whatever I have there. So after punching this in my calculator, I get 114,681 is equal to the sum of my first 14 terms. Now you might say, how did that get so big? First term was only 7, the third term was 28. But the thing is to remember that we are multiplying and getting larger numbers, and then we're continuing to add those together. And so even just, going to the 14th term is going to give us a very large number, let alone actually adding them up. All right, we're going to look at one last example here in this particular video. So this one, more interesting problem. We have a basketball that's dropped vertically. It reaches a height of 2 meters on the first bounce. The height of each subsequent bounce is 90% of the previous bounce. What height does it reach on the 8th bounce? Is part A. So I'm going to draw a quick sketch. So I drop a basketball, it bounces, and then on its first bounce, it reaches a height of 2 meters. And then it comes back down, and then it's 90% of what it was before. So we're going to not be quite as high, and then not quite as high, and not quite as high, 90% of what we had each and every time. And we want to know what height does it reach on the 8th bounce. Now, it doesn't say the word sum here. It doesn't say the word total or anything like that. So we're really just talking about a geometric sequence at this point, which means we're not going to use our S sub formula. We're going to use our U sub formula. So I'm going to have U sub n is equal to my first term, U sub 1, times my common ratio to the power of n minus 1. So I want the 8th bounce, so that'll be my 8th term, because again, it was 2 meters on the first bounce, not dropped from 2 meters and then had a first bounce. 2 meters really is the height of that first bounce, as I showed on my picture. So that's going to be my first term. My common ratio, well, it's the thing that I would multiply over and over again. And if I want to find 90% of something, I multiply by 0.9. Now, the most common wrong answer I would get there is people might say, oh, if you're finding a percentage of something, you divide. You can create a percentage by dividing, but once you have a percentage, like 50%, for example, you change it to a decimal. So let's take something we know, like 20. 50% or half of 20 would be 10. Well, if we divide by 0.5, we don't get 10. But if we multiply by 0.5, that's what actually gives us 10. So to find a percentage of something, change it to a decimal by moving that decimal point over twice, and then just multiply. And then our exponent is n, which we already know is 8 minus 1. So I'm going to plug all of this into the calculator. And I get a fairly long decimal for my 8th bounce. I am at 0.9 0.5659338. I believe that's an exact value because the calculator could have gone on longer than that. But at this point, I'm probably going to round. And when we round in this course, unless it says otherwise, we round to 3 significant figures. So my 8th term is going to be 0.95, and then that third significant digit, I need to look at what's happening behind it. So here's my 6, and behind it I have a 5, which means I need to round up, so 0.957, and this would have a label because it's a story problem, so it should be meters. And I'm just going to write this answer off to the side here. The 8th bounce is 0.957 meters. All right, on to part B. What is the total vertical distance traveled by the ball between the first and 6th time the ball hits the ground? All right, so we're dropping our ball. It hits the ground, and it goes up 2 meters, and then it comes back down. So I now have had 2 bounces, the first and the second bounce. Now I'm going to go up again. It won't be quite as high, and so that's my 3rd bounce. And now I'm going to bounce up again. This is my 4th bounce. Bounce up again. This is my 5th bounce. And do it one more time. My 7th. So I hit the ground 1, 2, 3, 4, 5, 6 times. 6 times hitting the ground. Now, how many actual bounce heights did I get to? Well, I had the first one here. I'll use a different color, which was the 2 meters. And then I had the 2nd one, 3rd one, 4th one, and 5th one. So I'm really looking for my 5th term. But it says total vertical distance. Now think about this. We were finding the height in the previous problem of like the 8th bounce. How high did it go? You know, as we continue on to our 7th and then 8th, like how high did it go? I don't want height this time. I want total vertical distance traveled. How much up and down? Well, on this first one, it actually didn't go up and down 2 meters. It went up 2 meters and then back down another 2 meters. And so it traveled 4 meters. And that's going to be this distance right here where it goes up and down. So it went up 2 meters, down 2 meters. So I'm going to think of my first term this time, instead of being 2, I'm going to think of it as being 4 meters. Another way you could have done this is we could have just thought of it as being 1, and then whatever answer we got, we could have doubled it, because we would have figured out the heights of all the up bounces being added together, and then we could have doubled it to also get those distances going the other direction. But I think this is as easy as any way, so we'll let our use of 1 be 4. Now again, we're trying to find the total distance traveled, and that keyword total is a synonym for sum, so we're going to use our S sub formula. So we have S sub n is equal to our u sub 1 times r to the n minus 1, not in an exponent, all divided by r minus 1. Let's start filling things in. So we decided, even though there's 6 bounces on the ground, that we only want 5 heights, essentially, that we're dealing with. So we're going to do sum of the first 5 terms of our sequence. We're going to let our first term be 4, which is double what we had because we have to go up and then back down. Our common ratio is still going to be 0.9, representing our 90% of travel of the first bounce. Our n is the same as it was before, which is the 5 right here. So we'll have 0.9 to the 5 power. And then it's all minus 1, and then 0.9 minus 1. And I had just gotten done on the last example saying it's really easy to subtract 1, and here we have a decimal with subtracting. Now, many of you would be like, oh, that's just negative 0.1, no big deal. But again, if you're not sure, you can type all this into the calculator just as written. You just have to remember to put an extra set of parentheses around the numerator and an extra set of parentheses around the denominator. And doing that, we can now just plug it all right into the calculator to find our total distance traveled up and down on those first 5 bounces, or in between the first and 6th bounce. So I'm going to plug it in my calculator now. And so I ended up with a value of 16.3804. And now I hadn't rounded anywhere up to this point, so I really could probably leave this exact. I could label it as meters, but because it is a little bit longer, we may want to round this, and so that would mean my value is 16, and if I round that third significant figure, there's an 8 after it, so it'd be 16.4 meters is approximately the total vertical distance traveled by the ball between the first and the sixth bounce. All right, so there are some applications of using our geometric series formulas.